Hey, so welcome back to Physical Science, guys. Mr. Brewer here. Uh, Perhaps might be good news. We're going to be shifting gears today related to what we'll be doing in physical science. We're actually going to begin to look at some of the ideas in chemistry that'll give you a little background that should carry you through some of the experience in 11th grade. So to give you a little background that you can build on, have a little foundation that you perhaps could work with later in your academic career. So let's see if we can get underway here with what we need to do. There we go. We got some very specific goals in mind for today's lesson. If we see here, one thing we ought to be able to do is to describe what atoms are kind of like in terms of their structure. They're made up of something called subatomic particles. You probably recognize those as protons, neutrons, and electrons. Three key terms: isotopes, atomic number, and mass number. These are words that you should sort of own before the end of this unit, and describe how the repulsive force that pushes things away, might create stability for the nucleus of the smaller kinds of nucleus of atoms compared to larger ones. So those are our very specific goals for the lesson. Let's get underway with some of the detail. So if we were to get started here, first of all, let's get rid of my face here. That's kind of distracting for me. There we go. Okay. One thing that we could think about is we could think about an analogy here. I like this analogy. Here we have a marble, and it's resting in the sky above the link where the Eagles play their home games. If we were to kind of visualize the marble as being the nucleus, the central part of an atom, and place that marble down here at the 50-yard line of the link, the marble would represent what we would call the nucleus. The entire rest of the stadium represents the rest of the atom. So generally what we're saying here is most of an atom, the nucleus is a really, really tiny amount. And what we like to think about is the region surrounding the nucleus is sometimes thought of as empty space. And that empty space is where those electrons revolve about in. Perhaps you recall maybe from seeing like a trailer for a cartoon called Jimmy Neutron, you recall seeing electrons firing around in different paths, and it creates something that we call energy levels when that happens, or the home where electrons live. So that's some specifics about the relative size of the nucleus compared to the rest of the atom. It's pretty tiny. Moving forward, if we're looking at the basic structure of the atom, it's made of individual parts: protons, neutrons, electrons. We call those subatomic particles. One thing that we want to kind of take a look at is how they're oriented or positioned. So obviously the nucleus is centrally located, even though this is not quite to scale. You see the nucleus is a little bit too large here, based on what I was talking about a moment ago. The nucleus is actually a very tiny part of the atom. So even though this is not to scale, it tells us what's in the nucleus: the protons and the neutrons. The electrons reside on these sort of ring-looking things, even though they're not technically rings. This is a model that allows us to view how electrons might occupy an atom. So we'll speak at some point in time about these kinds of models. So we call these energy levels. You might think about them as rings. They're the positions where electrons revolve about the nucleus. So we have some symbols that are often used. Electrons, E minus. The reason we use minus is electrons carry a charge that we tend to think of as a minus charge. Protons carry a charge that we tend to think of as a plus. The magnitude or the size of the charges are thought to be completely opposite of one another. So when we compare a proton to an electron, the charges are different in sign, but same in size. Neutron, when we think about neutrons, it kind of reminds you of the word neutral, meaning zero. They don't have a charge, so their net charge is zero, as seen in the table down here. So again, these symbols that I will commonly use: protons, P plus, neutrons, N0 for neutral, electrons, E minus for negative charge. So the structure of an atom, our nucleus, the tiniest part of the atom, right, is where our protons and neutrons are. The energy levels, that's where our electrons revolve about the nucleus. And that space where those electrons revolve about is typically empty space as those electrons move about. So some important key terms here that we're looking at that we should inherit from this lesson. There's something called atomic number, which relates to the number of protons. That gives the identity of every element. For example, lithium has atomic number 3. All lithium atoms have 3 protons. Carbon, however, atomic number 6. All carbon atoms have 6 protons. Oxygen, on the other hand, right, atomic number 8. So our identity is based on our number of protons, which we call the atomic number. There's another key term. It's called mass number. That's not specifically detailed on most periodic tables. So when we look at the square of an element for a periodic table for any specific element, mass number is typically not something that's provided, but its definition, it would be the total number of protons and neutrons in an atom. If we were to go back and look at this, it looks like I have 1, 2, 3, 4, 5, 6, 7, 8 total particles. The mass number of this atom would be 8 because the total parts in the nucleus make up 8. Isotopes, atoms of the same element, different numbers of neutrons. So basically what this tells us is there's a way that not all lithium atoms are identical to one another. Not all carbon atoms are identical to one another. Likewise, not all oxygen atoms are identical. How they can differ would be the number of neutrons. They have to have the same number of protons, atomic number, but the neutron count can be different. So we call those isotopes. So in review, lithium has atomic number 3, 3 protons in its nucleus. Carbon, atomic number 6, 6 protons. Oxygen, atomic number 8, 8 protons. What could vary amongst lithium atoms would be how many neutrons. And that would determine something called mass number, which we'll get to later in our lessons. So there are what we call specific isotopes of lithium atoms that differ somehow. Carbon atoms, isotopes of carbon atoms, and isotopes of oxygen atoms. Specifically isotopes, here's a lot of information about a way of thinking about isotopes, very visual, however. So here are 3 different isotopes of lithium, one called lithium-6, lithium-7, lithium-8. Well, let's take a look at how they are the same. Well, first of all, they're all lithium. So since they're all lithium, each of them have atomic number of 3. Notice that there is a red line running through lithium-8 where it says lithium-8 does not naturally occur, which generally tells us this isn't something we would find in nature. In order to have lithium-8, it would have to be man-made or created in a laboratory. So we have 2 common natural isotopes of lithium, lithium-6 and lithium-7. They're both lithium, atomic number 3. What's different is their mass number. So let's take a look specifically at how that varies. If I look at lithium-7, I see 1, 2, 3, 4 neutrons. If I look at lithium-6, I see 1, 2, 3. So total parts in the nucleus for lithium-6 are 6, mass number 6. For lithium-7, total parts in the nucleus, 7, mass number 7. Generally, when we think of atoms, atoms are thought to be electrically neutral, which really just means the number of protons for an atom should typically be equal to the number of electrons. So if we're speaking about atoms of lithium, all atoms of lithium have 3 electrons. That story will change when we speak about an idea called ions, but that lesson is reserved for another day. So specific idea that relates to isotopes, what they are, atoms of the same element. What differs is right here, the number of neutrons. Well, they'd be the same in a number of ways. First of all, they'd chemically behave the same. They would differ in mass. Lithium-7 would be heavier than lithium-6. So what we mean by heavier, if we go back and we take a look at ideas that we looked at, right? The mass is based on the number of protons and neutrons. Typically, look at this, it says that an electron mass is 1/2000th of the mass of a proton or a neutron. So it's almost like the electron mass doesn't really count. And sometimes we ignore that. And that's probably why, when we look at the definition, of this thing called mass number, it includes only the number of protons and neutrons. The mass of an electron's kind of thought to be insignificant. So moving forward, here we go. We go back to lithium-6 and lithium-7, right? Lithium-6 and 7, identical by the number of protons, different by the number of neutrons, identical by the number of electrons because we're speaking about atoms. So eventually we'll learn to relate symbols to these ideas that we call isotopes. A symbol for lithium-6 would have this 6/3. A symbol for lithium-7 would have this 7/3. Again, we'll reserve the specifics of that for another lesson. So final point about isotopes, most of the elements that exist in nature, they have a few, this should not say table, this should actually read stable. We'll fix that later in the lesson. So stable isotopes, and those stable isotopes are what occur in nature. So for lithium, lithium-6 and lithium-7 happen to be the stable, naturally occurring isotopes. So what determines whether or not an isotope is stable for an atom relates to something that, let's clear the drawing here. It relates to what I would call the ratio of protons to neutrons. So if we looked at an element called neon, neon on the periodic table is atomic number 20. Most neon atoms have 20 protons and 20 neutrons. Notice the ratio is 1 proton to 1 neutron, a 1-to-1 ratio. For the lighter elements, when there is a 1-to-1 ratio, we tend to have a very stable nucleus, meaning the nucleus will not wish to break apart, even though protons, as they get close to one another, they kind of react and push each other away. They have repulsive force. Well, when there's a tiny number of protons, that repulsive force is too weak to break apart a nucleus. So our nuclei of our smaller atoms tend to be very stable in a 1-to-1 ratio. So there is a graph here that shows 10 protons, 10 neutrons. A 10-to-10 ratio is the same as 1-to-1, pretty stable. 20 protons, 20 neutrons, pretty stable. The further and further we get, the heavier or the more protons we add to the nucleus of an atom, the more unstable atoms get, because that repulsive force between individual protons begins to build up. They begin to push each other away with a lot of force, and that allows a nucleus to become unstable or desire to split apart and break up. So this is our explanation why the nuclei of smaller atoms require sort of a ratio of 1-to-1 for protons to neutrons. But as atoms get heavier, like the element lead, notice there's no longer a 1-to-1 ratio. 82 protons compared to 125 neutrons. That ratio is clearly not 1-to-1 anymore. So there's kind of a graph here that says that that ratio changes away from this straight line of wanting to remain 1-to-1, and this is our reasoning for that. So the smaller nuclei, the 1-to-1 ratio is favored over here on the left of the graph. As we get closer to the right of the graph, we get larger nuclei, and that 1-to-1 ratio becomes less favorable. So these are the ideas that I wanted to make certain that we covered in today's lesson. So what you will do is you'll begin to follow up this lesson with some specifics that will get you to consider the structure of the atom. So we're going to use a software tool. That software tool is known as PHAT. Very good visual, application or visual app that will allow you to kind of take a look at atoms. So for today, that kind of concludes or summarizes this particular lesson that relates to the structure of the atom, the key terms, atomic number, mass number, and that key term, if we go back to the initial first slide of this lesson, we can kind of see that, our key terms, atomic number, mass number, isotopes are the things that I kind of wanted to make certain that we covered today with this particular lesson. So you may have noticed the Corona comb over going here. But that wraps up today's lesson. So for now, I'll bid you peace. Until the next time, Mr. Brewer signing out. Take care.